All right, welcome back to Blind Chess, where you watch the blind guy try to play chess. And on this one, we're going to listen to something, I guess, horrible. We'll listen to
Almost 30 years
this.
ago,
This is going to be
Andrew
horrible.
Wiles shook the mathematical
But
world by announcing a proof of Fermat's last theorem.
we'll play some more chess. I'm
The
feeling
ideas
good.
behind the proof
I think I got
transformed
all the...
algebraic
I
number
think I'm warmed up here.
In this program, we will explore how far we have come since then and how much further we have to go.
Pawn e4. Pawn d5.
Scandinavian
Pawn captures
defense.
d5. Knight f6. Knight c3.
But first, we have
Knight
to start
captures
from the beginning.
d5.
What is
Pawn
number
d4.
theory? One of the central problems in number theory is understanding
So this is
rational
goofy.
solutions to polynomial
Bishop
equations.
f5.
One of the first systematic studies of these equations was undertaken in the Arithmetica, a 3rd century text by the Greek scholar
Bishop
Diophantus.
d3.
For this reason, we now call such
Bishop
equations
captures d3.
Diophanting equations.
Queen
Perhaps
captures
the most
d3.
famous Diophanting equation in history is the equation
Pawn e6.
x squared equals 2. This equation has no solutions in rational numbers. Equivalently, the square root of 2 is irrational. Rumor has it that when the Greek mathematician
Knight f3.
Hippasus discovered this
So he had a nice
25
tactic here where he could
centuries
play
ago,
that.
Bishop
his fellow
b4.
Pythagoreans were so appalled they drowned him in the lake. The reputation of number theory as a tough subject hasn't changed much since then. Let's consider a second example. An arithmetic progression is a sequence of integers whose differences are the same. For example, 1, 25, 49, 73.
Castles
And so on.
kingside.
Here the common difference is 24. Notice that the first 3 integers here are all perfect squares,
Knight captures c3.
but the
Pawn
fourth one
captures
is not.
c3.
So, are there any arithmetic progressions of length 4
Bishop a5.
consisting of 4 distinct
So we
perfect
have
squares? If we call the squares
this
a squared
take, but then he has
b
take
squared,
there
c
after
squared, and d squared, then they would satisfy the equation
knight to d2.
b squared minus a squared equals c squared minus b squared equals d squared.
D squared.
c5 check.
This
Squared.
is a Diophanting equation.
D squad.
We call a solution to this
c6.
equation trivial when
Ooh.
all 4 squares are the same, and so the differences are all 0. This leads to the following
Queen
natural
captures
question.
b7.
Are there any non-trivial solutions? Almost 400 years ago, Pierre de Fermat proved that there were not. His proof, using infinite descent, was the starting point for modern number theory. So how does one study Diophanting equations? It turns out that one of the key ideas is to take the Diophanting equation and
Knight
count the
e7.
number of solutions
Knight
modulo
e7,
p
huh?
for all prime numbers p. One of the main goals of this program is to explain the reason why. Let's return to the equation x squared equals 2. Let's count the number of solutions to this equation modulo the prime p is equal to 3. 0 squared is equal to 0 mod 3. 1 squared is equal to 1 mod 3. And 2 squared is also equal to 1 mod 3. So there are no solutions.
Bishop d2.
If p equals 7, on the other hand, then there are 2 solutions. Plus or minus 3 squared is equal to 9 is congruent to 2 mod 7.
Castles kingside.
All right.
You can start tabulating the primes and the number of solutions bp to this equation modulo p for each prime p, and you get an infinite list of numbers bp. But how does this help?
Rook a
There are
b1.
2 fundamental reasons, both still conjectural, why point counting is a good thing to do. Understanding these 2 reasons goes a long way to understanding the last 50 years in number theory.
So I didn't
first
really have
reason
anything here
comes from
when his
combining
king was
2
there.
key
He
conjectural
well,
insights
Yeah,
path
yeah.
to Grothendieck
No.
and to Tate. These conjectures state the following.
It would have just kind of wasted some time, I
If you
think.
start with the
I don't
Diophantine
think.
equation X
Knight F5.
and consider
So
the
he
point
goes
counts
there.
BP for all primes P, then you can recover the original Diophantine equation from the numbers
I don't
BP.
see what that does.
In other words,
really.
there's no information lost by simply studying the set of numbers BP. To be more precise, from the point counts BP,
Knight
you can
E5.
recover something called the motive associated to the Diophantine equation. In many situations,
Ooh,
the
that's not
Diophantine
nice.
equation can be recovered from the motive.
This sucks. He can
This
take here.
equivalence on its own,
Man,
while interesting,
my tactics
really
are
not enough.
awful.
to justify studying point counts. The key observation, the basis for much of the Langlands program, is the following. For any Diophantine equation, there is another,
Dude.
completely different way
Yeah.
Knight
to
captures
generate
D4.
the same list of numbers, BP.
BP.
The reciprocity conjecture says
Knight
that given
C4.
any Diophantine equation, there is
Maybe
a
that's
shadowy
good.
object,
Is that
an
good?
automorphic form,
Probably not. He's got this
which
check.
generates the point counts in a completely different way. The definition of an automorphic form is
Knight
very
E2
complicated.
check.
I'm honestly not sure I understand it myself,
King
but at
H1.
least I can give some explicit examples. Consider the group Z mod 8Z star of integers prime to 8. This is an abelian group of order 4 with elements 1, 3, 5, and 7. There's a homomorphism from this group
Well, I pretty
So
much
the complex numbers-
trashed the position.
which sends
Gone from
1
up upon to
and
maybe
7.
down upon.
to 1 and sends 3 and 5 to -1. Chi is a particularly easy example of an automorphic form.
Man.
Let's consider the function AP, which takes a prime P and outputs chi P. And let's consider the function
Bishop
BP
captures C3.
to be 1 plus AP. For example, 3 goes to chi of 3 plus 1
Bishop
equal to
E3.
0. And 7 goes to chi of 7 plus 1 is equal to 2. For any prime P, it is a theorem that the numbers BP computed using this formula is exactly the same as the numbers BP on this list. This theorem is a special case of the reciprocity conjecture. In this case, it's actually a special case of the law of quadratic reciprocity proved by Gauss in 1798. Gauss's law of quadratic reciprocity is really the first non-trivial example of the Langlands program. It's also the reason why the word reciprocity is used for the general conjecture, even though Diophantine equations and automorphic
Queen
forms
H4.
don't look
Queen
anything alike,
H4,
except in
huh?
a few exceptional cases. Here is a second example. Take the following infinite product and expand it as a formal power series in Q. This is another example of an automorphic form. In fact, it's a modular form. Now consider the function BP, which takes a prime P bigger than 3 and outputs the following number. BP is P minus 1 times 1 plus P minus AP plus 1. For example, B of 5 is 4 times 1 plus 5 minus 2 plus 1 is equal to 33. And B7, by a similar computation, is equal to 49. These numbers turn out to be exactly the same as the number of solutions modulo P to Fermat's 4 squares equation, B squared minus A squared is c squared minus b squared is equal to d squared minus c squared, modulo p. For example, if p is equal to 5, the only solutions to this equation are the solutions in which all the a, b, and
Queen
c, d are all
C6.
0, or they're all plus or minus 1, or they're all plus or minus 2. And this makes
Rook
exactly
a d8.
33 solutions. This is another case in which the reciprocity conjecture is a theorem. Except in this case, it's not a theorem due to Gauss, but a special case of the Taniyama-Shimura conjecture. Although this particular example goes back to Shimura himself in the 60s. So what if we knew the full reciprocity conjecture? Could we answer all problems in number theory? It turns out that the reciprocity conjecture is only the beginning. One analogy is that reciprocity is like the periodic table. It's an important structural insight,
Bishop captures
but it's
a7.
only a starting point. In
Rook
chemistry,
d5.
there are many questions you can't even ask until you have the periodic table. Over the last 50 years, we have built a tower of conjectures which don't even make sense unless you assume reciprocity is true. So what consequences can we draw from reciprocity? Here's an example. We've seen
Knight e3.
that if you start with a Diophantine equation x, you get a set of point counts BP for all the prime numbers p. Using some simple rules,
Queen
you can
captures
define
h2
from
check.
this a sequence of numbers AP for
King
each prime number
captures
p,
h2.
Of course.
and then this
Rook
you can
h5
extend
checkmate.
That was
to
terrible.
a sequence of numbers an for each positive integer n. You can package these an all together into a new function
Pawn
called
d5.
an L function
Knight
by
captures
taking the
d5.
following
Bishop
infinite
f5.
sum.
Bishop d3.
an
Bishop captures
n to the
d3.
s from
Pawn
n
e6.
is 1 to
Knight
infinity.
f3. Bishop
If the real
b4.
part of s is big enough,
Castles
this
kingside.
converges,
Knight
and you get a
captures
well-defined
c3.
function in the right
Bishop
half of the
a5.
complex plane.
Queen b5
If, on
check.
the other hand,
Knight c6.
you start with an automorphic form
Queen
pi,
captures b7.
you can also
Knight
generate a
e7.
sequence of numbers an,
Bishop d2.
and you can also write down
Castles
an
kingside.
L function by the
Rook
same
ab1.
formula,
Knight f5.
except if you start with
Knight
an
e5.
automorphic form, you can prove that this L
Knight
function
captures
has an
d4.
analytic continuation,
Knight c4.
or possibly a meromorphic continuation
Knight captures
to the
d4.
entire complex plane. So one consequence of reciprocity is the following.
Pawn captures d4.
Given a Diophantine equation x, the L function
Bishop captures
has a
d2.
meromorphic
Yeah, I saw that,
continuation to
but-
the
Knight
entire
c6.
complex
Alright.
plane because the L function of x is
Queen
equal to the
d6.
L function of pi, where pi is associated to x by
Rook
reciprocity.
b5.
Moreover, from the L function, you can also recover the numbers AP. And so the L function should also know everything about the
So
original
weird.
Diophantine
Pawn
equation.
h6.
In this
Rook
way,
c5.
arithmetic problems about Diophantine equations
Pawn a5.
can potentially be converted into analytic problems about the L function.
Pawn
It's this
c3.
connection between arithmetic problems on
Pawn
the one
a4.
hand and analytic functions on the other, which is at the heart of the Langlands program.
Pawn g3.
Let's take the simplest possible Diophantine equation,
Bishop g5.
which is x is equal to 0.
Pawn h4.
Now this equation has exactly one
Bishop
solution
f6.
modulo p for every prime p. So in this case,
Rook e1.
AP
Stuff
is
like
equal
that.
to 1
All right,
for
I
all
played
primes p,
really bad.
and AN is also
try again.
equal to 1 for all n. So the L function of this Diophantine equation is simply the sum of 1 on n to the s for all
Pawn
positive
e4.
integers n.
Pawn e5.
This is precisely
Knight f3.
the Riemann zeta function.
Bishop c4. Bishop e7.
So the reciprocity conjecture,
Pawn d4.
proved in this case, implies that the
Pawn
zeta
captures
function
d4.
has a meromorphic
Knight
continuation
captures
to the
d4.
whole complex plane.
Pawn
In fact, it
d6.
has a pole at s equals 1. And now the idea is that the zeta function knows all about the equation x equals 0. So what does that mean? What arithmetic information can we extract from the zeta function? If you know anything about the zeta function,
Knight c3.
it's that its zeros
Knight
control the
f6.
distribution of prime numbers. The Riemann hypothesis makes a very strong prediction about where those zeros are. The Riemann hypothesis can be generalized to the L function of any Diophantine equation. But note that this generalized Riemann hypothesis doesn't even make sense until after one has proven reciprocity. But there are more basic relations between the zeta function and arithmetic than simply counting prime numbers. Here are two more examples. The fact that zeta of 0 is equal to -1/2 turns out to be equivalent to the fact that the integers have unique factorization. This is a special case
Knight captures
of the
c6.
Dirichlet class number formula,
Pawn captures
which relates
c6.
special values of
Castles
certain L
kingside.
functions associated to number fields to the orders of class groups. Here's something more exotic. We know that zeta of -1 is equal to -1/12. How does this statement translate into arithmetic?
Pawn h3.
It turns out that this is equivalent
Pawn
to the
h6.
following fact. Let SLNZ be the group of integer matrices with determinant 1. Then for n big enough, the Schur multiplier of this group has order 2. That is, there is a
Bishop
universal
e3.
extension
Bishop e6.
of this group, which is a central extension of degree 2, and all such central extensions are quotients of this group. So this is now a special case of the Birch-Tate conjecture and the relationships between algebraic K-groups on the one hand and the arithmetic of SLNZ on the other, and values of the Riemann zeta function. In particular, the order of the group K2 of Z is equal to 24 times zeta of -1
Bishop
is equal
d3.
to 2. Remember, you can't even begin to make sense of such a statement until after you know that reciprocity holds and that the L function is
Queen
defined,
d7.
and so you can make sense of these values. We now understand that these class number type formulas have conjectural generalizations to all Diophantine equations and all L functions.
Pawn f4.
Take the 4 squares in arithmetic progression equation. Remember that reciprocity is known in this case. This equation inside projective space defines an elliptic curve. The generalization of the class number formula in this case is the Birch and Swinnerton-Dyer conjecture. If we call this X, the Birch-Swinnerton-Dyer conjecture says that X has infinitely many rational points if and only if the L value of this L function at 1 is equal
Okay.
to 0.
I haven't been talking much because I'm
But you can rigorously compute, in this case,
not good.
that the L value
So
of
it
1
really doesn't
is
matter what I
equal
have
to
to say.
0.539, which is manifestly not 0.
Queen c8.
Now, by theorems of Colley-Vagan and
Pawn
Gross-Zeggia,
f5.
we know enough about the Birch-Swinnerton-Dyer
d7.
conjecture to deduce, in this case, that X has no non-trivial solutions. So, how do you prove reciprocity? If you have a Diophantine equation X, we see that we get
Pawn
a set
G4.
of point counts BP. On the other hand, if you have an automorphic form, you can also get a set of numbers BP.
Queen
So on the one
B7.
hand, you have Diophantine equations. On the other, you have automorphic forms. Now, on both sides, there are a set of natural invariants
Pawn B3.
which should match up on both
Queen
sides.
B4.
For example, for a Diophantine equation, you can take the primes of bad reduction. For example, if you take the equation x squared equals 2, this behaves badly at the prime p equals 2. This
Queen
reflects the
D2.
fact that p equals 2 is the only prime for which the two solutions, plus or minus root 2, somehow become the same modulo 2, but not modulo any other prime. If you fix the
Pawn
finally many
D5.
invariants on both sides, then you can prove on the automorphic side there will only be finitely many automorphic forms. So conjecturally, you expect
Pawn
on the
E5.
Diophantine equation side, there should only be finitely
Pawn
many
D4.
Diophantine equations and finitely many corresponding point counts. So to prove reciprocity, all you have to do is the following. First, show that given an automorphic form pi, there's a way of going from this to a Diophantine equation x, or possibly a set of point counts.
Dude.
Second, show that this map is a bijection. Let's say exactly the same thing in a much more fancy way. After you fix these invariants, Barry Mazur showed that you could capture the point counts by a ring which he called R. On the other hand, for automorphic forms, you can also understand them after you fix these invariants by another ring which you usually call T.
Bishop captures H6.
Thus, we're now reduced to 3 simple steps. 1, understand the ring R. 2, understand the ring T. For example, why given a pi, you get a sequence of point counts. Or in other words, why is there a map from R to T? And finally, 3, once you have these, understand why R is equal to T. The nice thing is that these 3 steps can often be considered quite separately. What Wiles and Taylor-Wiles did was come up with a general strategy to prove step 3, assuming you know enough about steps 1 and steps 2. This strategy is now called the Taylor-Wiles method. In the 90s, we did know enough about step 1 and step 2 in the special case of semi-stable elliptic curves in order to prove reciprocity for all such curves over Q, and hence for Wiles to deduce Fermat's last law.
So I don't.
There have
I
been a
think
number
maybe
of
I got
improvements
something
and
here.
important tweaks to the Taylor-Wiles method. The early work of Diamond and
Pawn
Fujiwara,
captures
He's gonna do
C3.
that.
the later work by
I'm gonna
Kissin
do
and
this.
Garrity,
Queen
and several
G5.
others. But the basic idea has stood the test of time remarkably well, and the Taylor-Wiles method remains the key tool for proving reciprocity to this day.
Queen C5 check.
That means that progress over the last 30 years has come from better understanding point counts on the one hand and better understanding automorphic forms on the other. Progress on these 2 problems is what we turn our attention to now.
Rook F2.
Number theorists study point counts in a more sophisticated way than just considering a set of point counts BP. Given a set of equations x and a fixed prime L, you can consider the Étale cohomology groups given by the Étale cohomology
Knight E8.
of x over q bar with coefficients in QL for some prime L. These are finite dimensional vector spaces, but they also have an action of the Galois group of Q.
I think I got to do that.
Which acts on V. Now, for every prime number P, the Galois group has a special
F6.
element called the Frobenius element, Frobenius P.
Bishop captures F6.
This element acts linearly on the finite dimensional vector space V, and if you take the trace of the linear map, you get back a number,
Pawn captures
which is
F6.
exactly
Bishop
number
captures
AP.
G5.
coming from the point counts. To be more precise, the Frobenius elements are really only defined up to conjugacy, but the trace of a matrix only depends on the conjugacy class. So the numbers AP are well defined. The key to understanding point counts turns out to be understanding these Galois representations. And to understand Galois representations, you really have to understand the structure of these Étale cohomology groups. So what is cohomology? One way to think about cohomology is in terms of differential forms. Again, it's useful to consider an example. Consider the equation x
Knight
times y
captures
equals 1.
F6.
Underlying this Diophantine
Bishop
equation,
captures F6.
there is a geometric object
Rook captures F6.
given by the complex solutions to this
King
equation.
G7.
If you know x, you know y, so you can just think about solutions to this equation as the set of all complex numbers x
Rook F1.
which are not equal to 0. Or in other words, the complex numbers with 0 removed.
Rook Fe8.
And we can draw this
Rook Ae1.
by the complex plane with the point 0 removed. An example of a differential on x is dz divided by z. Now if I take some loop, I can integrate the differential on that loop. And if the loop is contractible, then Cauchy's theorem says that the integral of this differential form over this loop is equal to 0.
Rook captures E1.
On the other hand, suppose instead I take
King
a loop
F6.
gamma, which goes clockwise around 0.
King F2.
Now if you integrate omega over this loop, you don't get 0. Instead, you get 2 pi r. In this case, the homology of C minus 0 is generated by the path, and the cohomology of C minus 0 is generated by this differential form. And there's a pairing between them, which takes a generator of one and the generator of the other and spits out 2 pi r. But this description of
Rook B8.
cohomology is given in terms of differentials and differential forms. Étale cohomology is
King
defined in a
G3.
very different way and is given in terms of finite covers. The one philosophy about cohomology
Rook
you should
G8.
know is that it should give the same answer however you define it
Rook
and however
F1
you
check.
compute it. One of the great early successes of the Grothendieck school was the very
King
definition
E7.
of Étale cohomology.
Rook E1 check.
Étale cohomology
King F6.
provided an algebraic definition of a cohomology group, which also knew about point counts. Showing that these Étale
E3.
cohomology groups had nice properties was the key to Deligne's proof of the Weil conjectures. But there is a second
Rook
way
E8.
to give an algebraic definition of cohomology in terms of differentials,
Rook
called
captures E8.
algebraic Durand cohomology.
Bishop captures E8.
The general philosophy now says that one should be able to
King F4.
reconstruct Étale cohomology together with all the point counts from algebraic Durand cohomology. Grothendieck understood that one should be able to do this, but he had no idea how to do it. And so he posed the question of how one can go from one cohomology group and produce the other. He called this process the mysterious functor. After clues
Pawn
in the
C5.
early work of Tate, the key to this puzzle was discovered by Jean-Marc Fontaine, who more or less invented the subject now called integral p-adic Hodge theorem.
Pawn H4.
One of the key goals of this theory,
Bishop c6.
now realized by the hard work of many people,
Pawn g5
was
check.
answering Grothendieck's question,
King g7.
explaining how to relate the different algebraic versions of cohomology to each other. Understanding what goes on in integral
King
p-adic
e5.
Hodge theory is a little hard to explain. After all, Grothendieck had no idea
Pawn
how it
a5.
worked. But one
Pawn
way to give a
a4.
cartoon characterization is as follows. Take this formula
Bishop f3.
of the integral of dz on z around the loop is equal to 2 pi I. Then you can ask, how can you make sense of this
King
equation
f4.
modulo p? It turns out that integral p-adic Hodge theory also gives a new and very rich structure to point counts.
Bishop
The
h5.
biggest step we have made in understanding point counts over the last 30 years
King
has
e5.
come directly from advances in
F3.
integral p-adic Hodge theory.
Bishop
Both of
e4.
these subjects have been closely intertwined. When Christoph Breuer found a new classification of finite flat group schemes,
Bishop
it led
d1.
directly to the proof
King
by
d5.
Breuer, Conrad, Diamond, and Taylor of the full reciprocity conjecture for all elliptic curves
Pawn
of the cube.
f6.
In the last 20 years, further insights
Pawn
by
captures
Breuer,
f6 check.
Nizar, Kolmez,
King captures
Kissen,
f6.
Emerton,
King
and many
captures
others
c5.
in p-adic Hodge theory
King e5.
has directly led to a better
Bishop
understanding
g6.
of point counts and to new theorems
Bishop e2.
in reciprocity.
Pawn h5. King f6. King d4.
So what about advances in understanding automorphic forms? Remember that the goal is to start with automorphic forms and link them to point counts. The strategy has always been to first relate automorphic forms to algebraic
Bishop
geometry
g4.
and then use algebraic geometry
King captures
to get to
c3.
point counts,
Bishop
or at least
e6.
get to Galois representations. Now, automorphic forms come in many different flavors. Sometimes the automorphic forms in question have a direct connection to algebraic geometry. But sometimes there is no apparent link to algebraic geometry at all.
Pawn b4.
Let's consider the automorphic forms conjecturally associated not to elliptic curves over the integers,
Pawn
which were
captures
considered by
b4
Wiles,
check.
but elliptic
captures
curves
b4.
over the Gaussian integers, zi. That is, we allow the
King
coefficients
g7.
to be Gaussian integers. We've seen
Pawn
two
a5.
examples of automorphic forms so far.
Bishop d5.
Now- We are ready for the third.
Pawn c4. Bishop b7. King c5.
This is a link consisting of three
Bishop
circles
f3.
called the Borromean rings. Consider the complement of this link in the three-sphere.
Pawn a6.
Theorems of Riley
Bishop
and Thurston
a8.
prove that this
Bishop
three-manifold
e8.
admits a metric of constant negative curvature and has the structure of a hyperbolic manifold.
Bishop
If you
f3.
start taking finite covers of this
a7.
manifold and then look at the cohomology
b7.
classes of these covers,
Bishop
then the
c6.
cohomology classes are given
Bishop
exactly
a8.
by the automorphic forms related to elliptic curves over the Gaussian integers.
About time, man. Let's check that one out.
More precisely, the automorphic forms are certain harmonic solutions to particular partial differential equations. The
Knight
fact that they are
f3.
harmonic
Knight
implies
c6.
by Durand theory
Bishop
that they can
e7.
be interpreted as
Pawn
classes in
captures
cohomology.
d4. Knight
But what is
captures
the link
d4.
between these cohomology
Pawn
classes in
d6.
algebraic geometry?
Knight c3.
The complement of
Knight
the Borromean
f6.
rings is very
Knight
much an
captures
object
c6.
in the world of Thurston
Pawn
and a
captures
long way
c6.
from the world of Grothendieck.
Castles kingside.
It turns out that there are
Pawn
seven-dimensional
h3.
manifolds, which are torus bundles over these hyperbolic
Pawn
three
h6.
manifolds. And those
So
seven-dimensional
far I'm playing pretty
manifolds
good.
are the boundaries of some
Bishop e3.
eight-dimensional manifolds. And those eight-dimensional manifolds
e6.
can be related directly to algebraic geometry. More precisely, they are the complex points of some four-dimensional algebraic varieties.
Bishop d3.
Peter Schulze found the correct
Still good.
technique
There was a lot
to
of good
exploit
bishop
this
moves there.
connection in
Queen
order to
d7.
link these automorphic forms to point counts.
I'm
Pawn
playing pretty
F4.
darn good here.
But Schultz's results weren't strong enough
Queen
for the
C8.
Taylor-Wiles method.
Wait,
Pawn
is that
F5.
good?
But
Queen
then
C8.
B3.
a second breakthrough. Cariani and
Pawn
Schultze
F5.
found a
So
key
that's
improvement to
slightly
Schultz's
inaccurate, but
previous work.
still good
The
move.
new method
Queen
gave
C8.
just
So,
enough
Queen
information
F3,
about
huh?
the automorphic forms in question, so that, with lots of hard work,
It's reasonable.
one could apply the Taylor-Wiles method.
Pawn
We
F5.
now know that
Bishop
all
D7.
elliptic curves over the
Pawn
Gaussian
G4.
integers satisfy
That's
at
not.
least
Yeah,
a
that
weak
didn't
version
feel
Bishop
right
D7.
either. Queen
The full
D2.
reciprocity conjecture of elliptic curves
Lining
over the
up
Gaussian
on
D2.
that
is now within
POW
reach.
right there.
Bishop D7. Pawn F5. Queen C8.
We can now prove reciprocity
B3
for
is a
very
really-
wide class of point counts
I
using
really
the
like that
Taylor-Wiles
move,
method.
huh?
This has led to
Alright.
many other spectacular
F5.
successes.
Bishop
New
D7.
cases of the Artin conjecture,
Pawn G4.
first proved by Buzzard,
Queen
Dickinson,
B7.
Shepard, Barron, and Taylor.
Pawn
the proof of
B3.
Serre's conjecture by Carré and
Queen
Winterberger.
B4.
The Sato-Tate
D2.
conjecture by combined work of Clausel,
Pawn D5.
Harris, Shepard, Barron, and Taylor.
So this
The
is all
modularity
good.
of all
Pawn
symmetric
E5.
powers of all modular
Pawn
forms
D4.
by Newton and Thorne.
I'm
Bishop
finding
captures
While
H6.
these results are spectacular, the problem
Finding the
is,
good stuff
from
here.
the
Pawn
perspective of
captures
an
C3.
outsider, this wide class of point counts doesn't always
Bishop
intersect
captures
with
H6.
Knight
examples
takes
coming from
G4.
diaphanting equations you might actually write down in real life.
So knight
For
takes
example,
G4 is a little better.
We now know that all regular self-dual motives over the rational numbers satisfy a weak form of reciprocity. But what are examples of diaphanting equations which satisfy this
Knight
condition?
captures G4.
If you ask an algebraic geometer on the street to come up with an example, they will most likely only come up with one: elliptic curves over Q. And we have
Knight
known how
D5.
to handle elliptic curves over Q
This is
for
pretty
almost 30
crazy.
years.
It's a queen
Fortunately,
sack.
We have
Queen
very
captures D2.
recently been able
Knight
to prove
captures
new
E7
reciprocity
check.
results for equations which turn up in real life.
What if
Let
he
me
goes
tell
here?
you about one such result now.
Well, it's not a queen
Recall
sack.
that one consequence
Bishop
of
captures
reciprocity
D2.
is that given a diaphanting
Knight
equation
captures
x,
E7 check.
the L function
King H7.
of x has
Bishop
a meromorphic
captures D2.
continuation to all of the complex plane. This particular prediction actually
captures
predates the
E5.
reciprocity conjecture. It goes by the name
Pawn
Oh,
F6
look at that.
check.
Hasave conjecture.
Knight captures E5. Pawn F6
It's not
check.
bad.
Again, so
Oh,
the
but that's
conjecture
hanging.
is that this
But in
is a
general,
meromorphic
Knight captures E5.
all right. It's
King
pretty
H7.
solid.
Queen captures D2.
on the complex planes.
Knight D5.
So,
Knight captures
for what
G4.
Is that
diaphanting
what the best
equation is
move? Yeah,
X,
queen
Captures
G5.
H6.
is the Hasave conjecture
Pawn
known?
captures C3.
Perhaps
And he
the
found the
simplest
best move
example
here.
of a
Pawn
diaphanting
captures
equation
C3.
is a
King
diaphanting equation in a
G2.
single variable,
But then
like
Queen
x
C5
equals 0,
check.
or x squared equals 2,
rook
or
E3.
more generally, the equation px equals 0
So
for some polynomial in one variable.
good enough.
Rook F2.
Even in this case, we
Knight
don't know the
E8.
full reciprocity conjecture.
And then F6 has
But we
got
do
to
know the
come.
Hasave conjecture
Bishop
So when the
captures
dimension of
F6. Pawn
is equal to
captures
0,
F6.
Is
this
that right?
follows
Queen
the work
captures
of
G5.
many people,
Bishop
including
captures
Hecke,
G5.
Artin,
Queen captures
and
G5.
Brower,
Bishop captures
And was
G5.
And that's just a technical
19
win
Knight
right there.
captures F6.
Once I'm up like
Pawn
two
captures
two
F6.
pawns in
Rook
material.
captures
captures
up on the
F6.
I mean, this is materially
That is,
equal, right?
consider polynomial equations
But we have two
Fx
pawns of
equals 0.
positional advantage.
in two variables.
And it's simple enough with the
integral
queens
functions.
off the board that it's
Now,
a
to take the
technical
complex solutions
technical
to
win
such an
here.
equation, you get a topological surface, which has
You'd think you
genus
should
G
grab the
for
open
some
E
non-negative
file
integer G.
here.
For example, if you take the
But his
equation
pawns
y
are so
squared
jacked.
equals px, and the degree of
King
px
G7.
is equal to
Rook
2g plus
F1.
1, or
Is that the
2g
best move
plus
there?
2,
Rook AFF1.
then the genus of x
Oh.
is equal to g.
Well, I didn't.
So for what g can we say anything about the Hasse-Weil conjecture?
Rook
There's essentially
F1.
one curve
See, that's fine. It's
of
there's
genus
so many.
0,
Rook F.
The point of this
given
is
by
to
the
be able to
projective
challenge the
rook
open
E1.
file.
and in this case, you could write the
One-
L
'cause
function
once-
Rook captures E1.
explicitly in terms
King
of the Riemann
F6.
zeta function, namely z
King
to s
F2.
And then it's
times
just a
zeta.
matter of kind of working it
Rook
out
G8.
here.
And so in this case,
I was just buying
Rook
some
F1
time
Hasse-Weil
here.
conjecture
King E7.
follows
He makes it easy on me
from
by
the fact about the
trading
Riemann
his
zeta
rook.
function.
Rook E8.
And so the Hasse-Weil conjecture
Rook
is
captures
It's
E8.
just a matter
theorem of
of
Riemann
Bishop captures E8.
capturing the center,
King F4.
from A
stopping
to
the
C5.
pawns, and then here
Pawn H4.
I could immediately
G5
play.
when g is equal to
King
1,
E5.
See, I don't know what the
We're
computer's
exactly
saying.
considering the case of
Who
elliptic
cares about all
curves.
that? Just go here,
Bishop
hence the
F3.
full Hasse-Weil conjecture in this
F4.
case
and
follows
it's
from Edward
over.
Wiles,
Bishop E4.
Taylor Wiles,
Bishop F3.
and Broy, Conrad, Diamond, Taylor.
How we doing on time? 41 minutes.
That last work from 2001.
That's probably good.
Now we come to the case of g is equal to 2.
Yeah, I've had enough chess. I think I've played like
For a long
3
time,
hours.
this was thought to
Did
be
3
beyond
episodes.
the reach of available techniques.
So, and I have no
But there is the
idea.
very recent work of boxer
Who knows what this guy's talking about?
Caligari,
I can't even see it when it's white
G,
screen like that. That's no fun.
and Piloni,
Blind
which
chess.
proves the full Hasse-Weil conjecture when g is equal to 2
I don't know. So
from 2021.
this is just technically
We usually
a
think
crushing
of
win,
algebraic
even
curves
though if we
as
count the
falling into a
material,
trichotomy of genus 0, genus 1, and genus at least 2.
the material is
spherical,
equal, but the
Euclidean,
quality
and
of the
hyperbolic.
material is
So this last result
just a lot better.
sounds very promising, but it is a little
All
misleading
these pawns.
for questions
Excuse
of
me, I'm
reciprocity.
getting tired. All
We
these
now
pawns are
understand that instead of a trichotomy,
disconnected and
there is
broken,
really a
and on
tetrachotomy
dark squares, so it's
corresponding
like
to the cases of genus 0,
difficult for
genus
him.
1,
Yeah, I'd say
genus 2, and genus bigger than 2. From our
the
perspective,
fastest way I
the
see
case
to
of
challenge
genus
all of
3
it
seems
is to go
hopeless
here so
by
your
all
king
current
can go over
reference.
here and eat
The
pawns.
automorphic forms one has to understand seem completely inaccessible.
All right, that's awesome.
Unlike
Is
the
this guy
cases
done?
we've seen so far, where these
Should we let
forms
this guy
can be
finish?
interpreted as cohomology
Let's listen.
classes,
Let this guy finish his
when g
thought.
is at least 3, they correspond to certain solutions to differential equations, which have no
This stuff is
known
way
geometric
abstract,
interpretation.
and I have no idea what he's
In
talking
fact,
about.
we can't even rigorously compute a single example.
No,
let
he
alone
can't.
relate
They have
to
no
algebraic
examples
geometry
ever.
Or prove reciprocity.
Thanks, man.
And yet, in 1993, nobody besides Andrew Wiles
BP
had
and
any
G
idea
is
at
3
all
and
how
no
to prove
examples.
reciprocity for elliptic curves
We have
over
no
G.
idea what anyone's talking about.
Mathematics is full of surprises.
Oh, yes, it's full of shit. Pardon my French, but I like examples. Anyway, have a wonderful day, and I'll come back at you with some more chess later. Bye for now.